Let's go ahead and look at one last example that actually has to do with the last corollary that we talked about. So, if we can recall just on the last video that we were talking about here, our previous corollary actually wasn't even this, but just don't mind that weird blue marking that someone else wrote in there. Not Mr. Wee. Okay. So it basically said if you have three parallel lines and they cut up a transversal, much this way as AC is the transversal, A to C is the transversal, and you cut up AC into two different parts because of these three different parallel lines in such a way that AB and BC make a ratio. Let's say it makes a ratio of 1/2. Guess what? If you create another transversal coming at a much steeper angle or even like a much more vertical angle, basically what it's saying is no matter what, with those three same parallel lines making the ratio of 1/2 between AB and BC, you're going to have the exact same ratio occurring with EF to FG. And to take that one step further, if you have three parallel lines that actually cut up a segment AC into two congruent parts on one transversal, if you look at the other transversal, it too is going to create two different parts that are congruent as well on the other transversal. So let's take a look at this problem here. So go ahead and write this down. You can pause this and kind of take a minute to write this problem down here. But basically, here's a situation spelled out for you. You have three parallel lines, JM, KP, and LQ. They hit this transversal in such a way, MQ is the transversal here, in such a way where MP is going to be congruent to PQ. That's what we have here. And we have MP and PQ being equal to each other, and they have these side lengths. MP is 3y plus 8, and PQ is 5y minus 7. JK and KL are also split, or basically this transversal J to L is also split by the same three transversals. You might be able to see where we're going with this. I'm sorry, it's being split up by the three parallel lines. Okay, again, JL is the transversal. I'm sorry to clarify. These three lines are parallel lines cutting this transversal. So these three parallel lines are cutting MQ in such a way that MP and PQ are congruent. So my task is to find X and Y. Y is going to be pretty simple. If the MP is congruent to PQ by the property of, or what is it? I think a property of congruence. Not only are they congruent, but they will be equal in length. So when I talk about line length or line segment length, I don't need to indicate that we're talking about the line anymore. We're just talking about the value of MP, which is 3y plus 8, as stated here, is going to be equal to 5y minus 7. So we set that equal to each other. 3y minus plus 8 is equal to 5y minus 7. We simply solve for y by subtracting 3y from both sides. This is just basic algebra. Then you're going to have 8 is equal to 2y minus 7. You add 7 to both sides. Not a big deal. And then you have 2y is equal to 15, or 15 is equal to 2y. We divide both sides by 2, and you should get that 7.5 is equal to y. Not a big deal. But I also asked you to find out y. If you notice, that coincidentally happens to be in the values of JK and KL. So I know that these two, we're going to have to set up these two side lengths to find out x, the value for x. And we also know from the second corollary that if you look back again on the second corollary, 9-2, let me see if you can read that here. 9-2, that if you have three parallel lines cutting a transversal in such a way where that transversal is now cut up into two perfect congruent parts, if you drew another transversal on the other end or wherever else that hits these three parallel lines, then it too will be cut up into two congruent parts. So let's use that logic for this problem here. It's pretty simple. If MP in PQ are now congruent because it's cut up by these three parallel lines. Then JL, this transversal, is also going to be cut up into two congruent parts as well, meaning JK is going to be congruent to KL. So why don't we actually put that down? JK is actually going to be congruent to KL, making them equal in actual value. Okay, so they're congruent in both shape and size. Now we're talking about just the measure of the size, which is, in this case, JK, if you looked up here, is 6x minus 5. I'm running out of pen now. And then KL is going to be 4x plus 3. And then you can kind of see what you need to do to solve for x. You just use some basic algebra by isolating the x. You subtract 4x from both sides, then you have 2x, only from like terms with x's in them. 2x minus 5 is equal to 3. You add 5 to both sides to isolate x. To solve for the singular value of x, that's 2x is equal to 8. And then you divide both sides by 2 to again isolate that variable of x by itself, and you have x is equal to 4, and that is your final solution. Okay, guys, thank you guys for joining me for 9.4. And join me again for 9.5. As I believe now we discuss, let's see, let's take a look into 9.5. We're just going to look at more stuff with triangles that are similar, and then we're going to call it a day. Okay, guys, thank you guys for joining me. Bye.